Great. So welcome everybody to today's edition of the Western Hemisphere Virtual Symplectic Seminar. We're really happy to have Richard Hind with us today from Notre Dame, and he's going to tell us about symplectic manifolds without boundary and packing failure.
All right. Well, thank you very much for the invitation. Okay, can you see my screen? It's okay?
Yep, looks good.
Okay. All right. So I'd like to talk about this theorem here. So this is all joint work with Dan Cristofaro-Gardiner. Okay. All right. So I'd like to talk about this. So what we're saying is there's an open subset in the standard Euclidean space. It's toric, so it's invariant under the usual torus action. It has smooth boundary. It is, I'm going to write it down in a little bit. It is unbounded, but it's symplectomorphic to a bounded domain. However, it's not symplectomorphic to the interior of any compact symplectic manifold with smooth boundary. And also, if you take any collection of any finite, okay, let's just say, to make it concrete, if we say a finite collection of domains in R4 with piecewise smooth boundary and total volume equal to the volume of X, then there is no symplectic embedding from the disjoint union of those domains into X, even if you scale them down a little bit. So this second condition means there are no volume filling symplectic embeddings, or no full packings, I guess would be another way of saying it, for X. So, okay, so I want to talk about this. So I suppose you can argue whether or not this is surprising. So, well, I don't know. I suppose if your intuition comes from Riemannian geometry, you might say it'd be a shock if there were any volume filling embeddings at all for any X. But it turns out a large collection of symplectic manifolds do admit volume filling embeddings, at least from large numbers of balls. So right, yeah, so it's well, anyway, yeah, so I don't know. So you can argue both ways. But in any case, it seems to be new, and we couldn't think of an elementary argument for any of this. So we're going to use the subleading asymptotics of the ECH capacities. All right, so that's going to be the proof. Okay, all right, so that's the statement. So I'll just fill in some of the words here. Okay, all right, so it's a toric domain. So, all right, so what are these? All right, so mu here is just the regular moment map. We say a domain is toric, it's invariant under the torus action. It's just going to be the pullback of some subset of R2 by the moments map. And this covers things like balls, ellipsoids, polydiscs. All right, so balls and ellipsoids are just the pre-images of triangles. It's isosceles, I guess, if it's a ball. The polydisc is the pre-image of a rectangle. And then there's this notation that you say a toric domain is convex or concave if it's the region, well, if it's generated by the region under the graph of a concave or convex function. Okay, so this is fairly well known then, right? So those are toric domains. Okay, so just an easy way to describe subsets of R4. All right, and then this is our X here. All right, so I need some, all right, okay, so P is a number between 1 and 2, strictly, okay, and then that's our X, right? So it's just the area under the graph. I'm using R and S for, there's a reason for this, but right, so I'm using R and S for coordinates on R2, and then it's just the area under the graph of that function. All right, it's a smooth function, so this is it's a convex function, so this is a concave toric domain. It has smooth boundary. Finite volume exactly because P is bigger than 1. All right, so that's the assumption that P is bigger than 1. So this is a finite volume domain. Of course, it's unbounded. This function is asymptotic to 0, but never hits 0. So it's unbounded, but nevertheless, we can prove that it's it is symplectomorphic to a bounded open set. All right, so this is saying something, right? So there's just a remark at the bottom of the page. Not all toric domains of finite volume are symplectomorphic to bounded open sets. All right, so examples of this, I think, originally come from motivated by Hermann. So the idea is you can just take a small neighborhood of the diagonal, and that contains monotone Lagrangian tori of a very large area class. And actually, it goes back to work of Sakharov, maybe in the 90s, saying that such things can't embed even in cylinders. All right, okay, so that's our set. So it's a sort of reasonable looking domain, but okay, anyway, okay, so that's what we're going to study. So that's our set X. Okay, so what's next? All right, so a few slides about packing. All right, so these are general concepts, I guess. All right, so just fix any symplectic manifold of finite volume, and then something I'm going to try to pack it by, which is going to be D. So in principle, D could be any, I guess, open symplectic manifold, usually a subset of Euclidean space. And then you can define these packing numbers, which are supposed to quantify the symplectic embedding problem for disjoint unions of D. Okay. So, all right, so the nth packing number tells you how large a proportion of the volume of M you can occupy by a symplectic embedding of disjoint unions of D with some scaling. All right. So it's right. So how much of M can be filled by disjoint unions of copies of suitably scaled D. All right. Okay, so that's the packing number, and most of the work here is done when you just take D to be a ball. All right, so I guess that's the most natural choice here. Okay, and then I'll simplify the notation a little bit in the ball case. All right, and then maybe the first sort of asymptotic results here. So of course you can sort of write things like Gromov's non-squeezing in terms of inequalities on packing numbers, but the first maybe asymptotic result is due to McDuff and Polderovich, and they say at least as n goes to infinity, these packing numbers are going to converge to 1. All right, so this is at least in dimension 4, this is very explicit, so you can almost write it down. So this is saying you can fill take any symplectic manifold of finite volume, you can fill an arbitrarily large proportion of the volume by a sufficiently large number of embedded balls, disjoint embedded balls. Okay, so that's McDuff and Polderovich. So at least asymptotically, you can fill up your manifolds by balls. All right, but then there's a stronger notion here. So we say M has packing stability if these packing numbers are identically 1 for all n sufficiently large. So in principle, this is a stronger notion. So this is now saying, okay, you can fill up an arbitrarily large percentage of the volume of M by embeddings of a fixed number of balls. All right, as long as that fixed number is large enough. All right, so that's packing stability. All right, so it seems a strong condition. Then it turns out actually a lot of manifolds do have packing stability. So it's a symplectic phenomenon. We do have packing stability. So for example, all right, so the first one I think is due to Buran, the end of the 90s. So any closed symplectic form manifold with rational, so I want the symplectic form to be rational. In other words, so that's a rational cohomology class. They all have packing stability. Then, right, so I generalize that to work with Olga Busa. So in fact, you can drop the 4 here. So all rational closed rational symplectic manifolds in any dimension have packing stability. Then a little bit later, if you go back to dimension 4, you can drop the rational assumption as well. So in fact, all closed form manifolds have packing stability. That's joint work with Opstein. And then Okay, there's still mainly closed manifolds. Polydiscs were included, but you can generalize the polydisc. So so convex toric domains in R4 also have packing stability. So there's quite a list here. So last one, Cristofaro-Gardiner, Holm, Maldini, and Perez, quite recently. Okay, so that's somehow our argument. So packing stability is quite a common phenomenon. There's an influential survey paper which appeared in 2007, right? Chilibak-Hoffer, Lachev, and Schlenk. Right, and they asked in general which symplectic manifolds and which packing subsets. Right, so for which pairs do we have packing stability? Well, so that appeared in 2007. I don't know if he's here, but anyway, it was possible to conjecture later, so maybe in light of some of this, that maybe all symplectic manifolds have symplectic packing stability for all choices of D. So in principle, that was open.
Sorry, Richard, a quick question. If I take a particular instance of any of these 4 classes of symplectic manifolds, is it just the existence of N naught, or is there some way of reading off from knowing something about the manifold what is a valid choice of N naught?
Well, that's a very good question. I mean, okay, at least, well, right. I thought about this. I think a lot of these constructions are sort of constructive. So you can get bounds on N0. So if you're given a closed 4 manifold, I can kind of, if I know enough about it, I can try and bound N0. But getting the optimal bound, so you say the packing number is the smallest number of balls you need to completely fill. And that is typically open in higher dimensions. So it's known for the 4-dimensional ball, I think it's 9. But for the 6-dimensional ball, it's completely open. I think it's some number between 5 and 22, but I don't know what it is. So typically getting sharp bounds on this is a very difficult question. It's essentially like, you're sort of solving the symplectic embedding problem. It's hard to do. So all of these results are sort of asymptotic. Just, there's some construction that works if you have a big enough number of balls. But precise bounds are very interesting. And typically, okay, especially in high dimensions. All right, yeah, so it's a very interesting question. Okay, all right, so just a little comment here. You can ask for an even stronger notion of packing stability. So saying the packing number is 1, so say if the nth packing number is 1, that means I can fill an arbitrarily large proportion of the volume by embeddings of a disjoint union of n balls. There's a stronger notion which holds for closed 4 manifolds, saying you can actually get embeddings which are volume filling. So you can actually find a symplectic embedding which fills up all the volume of n. All right, so this is about the strongest statement for closed 4 manifolds. There's just any 4 manifold has a number associated to it, lambda. And if you take any collection of balls, each of them, I think finite collection of balls, each of them has capacity less than lambda, then there's a symplectic embedding if and only if there's no volume obstruction. Even if the volume obstruction is an equality, you can still get an embedding. Remember, my definition of balls is open, right? So this would be false for closed balls, but for open balls, you can completely fill up the volume in a 4 manifold, a closed 4 manifold. Anyway, right, so just to restate our theorem then, so we are saying that for this domain X, any notion of packing stability fails. So in fact, all of the packing numbers are strictly less than 1. You can take D to be a ball or any bounded subset of R4, as long as it has piecewise smooth boundary. That's it. So we need, of course, we need some assumption on D, because you can't just take D equals X, right? So X is a bounded subset of R4. So I don't want to take that, but anything with piecewise smooth boundary is fine. Okay, then all packing numbers are strictly less than 1. So that's what we're saying. All right, okay. I have a chat. Do I have to worry about that? What does this say?
No, that was just
Oh,
me.
that's you. Okay. All right. All right. Okay. All right. So I want to talk about this. Okay. So as I was saying, so we, right, yeah. So we struggled. We don't know how to an elementary proof of this, or even using just maybe a single obstruction. So we're going to use asymptotics of ECH. So okay. So I think now I have a few slides about that. All right. And this is embedded contact homology. So this, all right. So this was defined and developed by Michael Hutchings, and also all of the, I think, most of the fundamental results here are all due to him. So, so anyway, so what you can do? So to any symplectic manifold, you can associate a sequence of numbers called the ECH capacities. It's a non-decreasing sequence, starts at 0. I couldn't tell you exactly what these things are. Maybe that's why I don't want to do that. But they do have various nice properties, which make them very amenable to computation. So for instance, well, they're monotonic under symplectic embeddings. So that's kind of the key property of capacities. And also they're computed in various cases, in particular for balls. All right, so so we'll need this formula. All right, so the ECH capacities of a ball, they're all multiples of the capacity. And if you want to know the kth ECH capacity, the multiple you need is the largest d, where d squared plus d is less than 2k, less than or equal to 2k. All right, so there's a explicit formula for the ECH capacities of a ball. Also, there's a formula for disjoint unions. All right. Okay, so you have a disjoint union of symplectic manifolds, then right, then the kth ECH capacity is a supremum over sums of capacities of the individual domains, right? Where the individual capacities have to sum to k. All right, so those are two results we'll be using. All right. Okay. Well, right. So we're especially interested in the case where so my domain is going to be presumably a large disjoint union of balls or some other bounded domains. But I'm assuming maybe the total volume of the domain is equal to the total volume of X. Right. So this results here, 2015, right? So due to Dan, Michael Hutchings, and Vinicius Ramos. So it's saying that the ECH capacities see the volume, right? So the first order asymptotics of the ECH capacities converge to the volume. Well, times square root of k. Okay, so somehow just the first order asymptotics of ECH aren't going to obstruct volume preserving embeddings. Well, it's still sort of very interesting results, but anyway, so we need a little bit more detailed information, and the idea is to use the subleading asymptotics, and to get at those, I want to introduce the error term. So all right, so when k is large, the first order approximation would be just ck is twice square root of k times the volume. So right, so the error term is going to be ck minus that expression. Okay, so that's called the error term. And now we'd also like to get estimates on that. Okay, so there's been work done here also. Right, and the results, so we're motivated by another result of Hutchings, right? So it's so if you take a bounded domain with some constraints, we say if it has smooth boundary, then this error term is of order k to the quarter. Okay, so that's so we know quite a bit about the asymptotics of putting all this together. We know quite a bit about the asymptotics of ECH capacities in these cases. All right, so that's ECH. Okay, right. So So in principle, then, right. So we have the disjoint union property. We have the computation for balls. So we're interested in getting embedding obstructions. So we need to get estimates on the error term of the ECH capacities for our X. Right. And it turns out there's also a method to do that. Okay, so it's all right. So I'll just sort of outline how that goes. All right. So it's so if you take a concave toric domain, it has a weight sequence. So this is a sequence of non-negative numbers. And it turns out the ECH capacities of the concave toric domain are the ECH capacities of the disjoint union of the corresponding balls. Okay, so then how to find the weight sequence? All right, so for the first term, you take the biggest, the largest A, such that B of A sits inside the image of the toric domain under the moment map. All right, so remember, omega is the subset of R2, which generates the toric domain. So, and B of A, remember, is it's the subset of R2, which pulls back to give the ball. So, in other words, A1 is the largest ball which embeds in our toric domain by inclusion. Okay, so that's the first term of the weight sequence. Then you take your toric domain, you remove that triangle, right? So B of A is a triangle which hits the axes, it's A0, 0, A. You remove that triangle. There's going to be two components left. And it turns out they're both also concave toric domains under, if you act by translation, and SL2Z. Okay, and then you sort of define the weight sequence recursively by, kind of sort of iterating this construction, right? So finding the largest ball sitting inside these smaller concave toric domains. All right, so anyway, let's get the hang of this. So I've got a little picture here. So that's it. So this, okay, so that's supposed to explain. That's supposed to explain weight sequences. So the top figure here, that's my original omega, right? It's a concave toric domain. The first thing I do, I take out the biggest triangle that I can fit. So that's the A1. And when you remove that, you're going to be left with two smaller toric domains, omega 2, omega 3. So for our estimates, we're just going to focus on the omega 3. Right, so the claim is that omega 3 is also a concave toric domain. Right, so you see it there, right? So it's sort of the right-hand tail. Omega 3 is also a toric domain. So to see that, you translate by A1 to the left, right? So put the intersection with the R axis at the origin, and then you act by that matrix. All right, and that converts it to a concave toric domain. All right, so the interesting thing here then, so if we look at the graph of the original omega, so that's S equals F of R. If you look at the point with slope -0.5 on that graph, okay, so now on our graph, that's a well-defined point. Then when you do this, when you act by this affine group, that point is going to become, well, it's going to become a point on the graph of the new concave toric domain, but now the slope is going to be -1. So in other words, that point is going to lie exactly on the triangle of size A2, where A2 is another weight. All right. Okay, and in fact, A2, I'm just looking at this, I know what A2, I don't know what A2 is, but it's at least the value of the function at the point where the slope was -0.5. Right. So this action of SL2Z preserves the S coordinate. Right. So the A2 is going to be at least the value of the function where at the point where the slope is -0.5. All right, so okay, so that's weight sequences. So just kind of what I claim we can get from that. So this is sort of a rough estimate. Well, okay. So you keep doing this. Let's just focus on just keep doing this procedure. Focus on the part of the concave toric domain that's the tail going off to the right. So then what you see is if we find the point on the graph of F with slope -1/n, then there's going to be a term in the weight sequence whose capacity is at least F of A. All right. So I'm not saying these terms are appearing in order. We might be throwing out a lot of terms here, but at least we're going to get weights of these various capacities. So, okay. So then let's put the weights in decreasing order. And then in specific cases, this is an easy way to get estimates on the size of the weights. Okay, so you just find the points where the slope is -1/n, and then you're getting a weight of that value. All right, so so you plug in our f. Okay, you compute, you work out the slope, you work out the value at those points, and then you come up with this formula. This is a lower bound for the weights of our domain X. Right. All right, so pretty soon we're going to be ignoring constants. So this looks like 1/i to the p over p plus 1. So it's so in fact, so thinking about these weight sequences, the total volume of the balls corresponding to the weight sequence is going to be the volume of X. So in other words, the sum of a squared over 2 is going to converge to the volume of X. But here, the sum of the weights themselves form a divergent sum. All right. So p over p plus 1 in our case is between what is it, a third and a half and 2/3. So this is a divergent sequence. Right. Anyway, okay. So those are the weights. All right, and that's it. So the idea is for our domain, okay, it has finite volume, but nevertheless the weights have very slow decay. So that's kind of what we're using here. All right. Okay. So now, all right. So this is the estimate. All right. So when k is very large, well, we need that. Well, at least when k is bigger than 1, you could say here. So c is just going to be any constant which is independent of k. Right? So in particular, it could depend on x, anything else, but independent of k. Then we're saying that the error terms are bounded above by negative k to the 1/2p. All right. So this is really our key estimate. All right, which essentially it's a formal consequence of everything I've said, right? So of the disjoint union property in the computation for balls and what we know about the weight sequence. So this is at this point, this is just putting things together, but all right, but I'm afraid, but since it's our key estimate, I thought I would go through the steps. So okay, so right, so this is the plan. So this is the main sort of estimate here. So we'll kind of try and go through this. All right, so essentially just reviewing what we have then. All right, so it's okay, so we have a formula. Right, okay. All right, so I have a formula for the kth capacity in terms of the disjoint union of the balls. Okay, then we feed in, right, to work out the capacity of the disjoint union of the balls, we use the disjoint union property. Okay, that's written out here in the first formula. Right, so the kth capacity of X is it's a sum of capacities of balls in the weight sequence, and then we've got to recall the capacity of balls. So if I want to work out the kth capacity of a ball, I need to find the largest d where d squared plus d is less than 2k, less than or equal to 2k. All right, so putting this together, so right, so this sum is going to be a sum of multiples of the capacities and multiples of the weights, sorry. And to get the maximum, I want to choose the di to sort of to be maximizers of this optimization problem. All right, so I'm trying to maximize this thing, the sum of ai, mi I've got here, where the constraint is that the sum of the m squared plus m's has to be less than 2k. All right, so if you, if you find any elements of that set, they give you a candidate for the maximum of the sums of the capacities, and then right, and then if we take di to be the optimizer, then I'm going to get the kth capacity of d. All right, does that make sense? Any questions here? So it's not a contorted proof, right? We're just doing this by brute force here. Right, plugging in the formulas. However, there's some things you can notice about this, right? So if I order the AIs to be non-increasing, I'm also going to get candidate sequences DI if I just rearrange the order of the DIs. So it's in our interest to put the largest DIs in front of the largest AIs, right, in order to get a maximum. So if the AIs are non-increasing, then the DIs should be non-increasing as well. Also, since the capacities have to sum to K, well, okay, actually, you can even say K over 2 here, I think. Anyway, so only K of the KIs can be non-zero. So certainly the DIs are going to be 0 beyond a certain point, right? We have to get better estimates on that, but anyway. So the DIs, it's a non-increasing sequence, and for sure after K terms, they're all going to be 0. All right, okay, so that's right. So that's the formula for the capacity. Okay, now we want to plug in some estimates to get the error term. Okay, so since it's a maximizer, right, we have this formula, right? So the sum of the DI squared plus DI is 2K. We talked about the volume formula, right? Right, the sum of the squares of the weights give you the volume, and then you can plug that into Cauchy-Schwarz, and we get this formula. All right, so that's which is quite nice. All right, so it straight away gives you a lower bound on the first order asymptotics for the ECH. All right, so it's Cauchy-Schwarz. All right, and then okay, so right, so that then once I have that estimate, I can plug in to get an estimate for the error term. Right, so by definition, the error term is the right, it's the capacity minus this 2 square root K times the volume. Right, and now I have a lower bound for the volume, right, which is going to give me an upper bound for EK, right, because of the negative sign. So the EK is going to be negative, is the idea, right? So I'm very careful here. All right, okay, so that's right, so that's it. Right, so I'm just plugging in the formula for CK, which is AI times DI, and then subtracting off the estimate for the volume, and then you get that. So, okay, so this is an estimate for EK, and my goal is to show that EK is very negative. Right. Okay, so looking at this then, right, so as far as these terms go, this expression DI minus the square root, remember the DIs are integers, and if the DIs are not 0, then in fact this whole factor is at least square root of 2 minus 1. All right, so those factors, at least when the DIs are non-zero, are nicely bounded. Well, they're bounded above by a negative number. And then remember that the AIs themselves, though, we've arranged that the AIs is a divergent sum. Okay, so if a lot of the DIs were non-zero, then I'm going to get a lot of terms in a divergent sum, and I'm going to get right, I'm going to be able to prove that the EKs are very negative. So that's kind of the motivation here. All right. So the game now then, so we just essentially have to show that a lot of these DIs are going to be non-zero. Correct? That's hopefully that's correct. Okay, so that's all right. Maybe I'm racing through here. Anyway, that's all right. So that's the goal. So right, so we have the weight sequence, we have these this optimizing factors DI. And then, right, I'm trying to show that a lot of them are going to be non-zero. Okay. All right. So okay. So the DIs, they're a non-increasing sequence. So all right. So it's so I'm interested in the right. So to work out how many are non-zero, we might as well try and find the smallest I where DI is 0. Okay. So I'm going to call that capital I, which in principle depends on K. Okay. Right, and then there's a little trick at this point. All right, so I'm interested in estimates on IK, ideally lower bounds on that. So let's just pick some J smaller than IK. So DJ is not going to be 0. And then we consider a new sequence of Ds. All right, so D prime. So the D prime, I'm going to set D prime J to be just DJ minus 1. Okay, so that's what's happening in the jth entry. So, okay, so then, all right, so then if we look at this little note here, so then DJ prime squared plus DJ prime, it's going to be smaller than DJ squared plus DJ, but it's going to be smaller by exactly 2 DJ. All right, so if I replace DJ by DJ minus 1, I've essentially, I can put ones in DJ of the entries which were originally 0 and keep the sum of the d squareds plus d still the same. All right, so that's our game. So we just change the sequence. So knock 1 off DJ and add on the corresponding DJ ones when you go past IK. All right, that's still going to be a candidate sequence. All right, so the sum of the squares plus DJ is still going to be 2k. All right, so it's still a candidate sequence, but the assumption was that our original DJs were maximizers. So therefore, the capacity estimate has to go down. Okay, so in other words, the amount we lose by this maneuver, which is going to be AJ, because I'm taking one less multiple of AJ, right? So the amount I lose has to be more than the amount we gain, right? And the amount we gain is this sum, right? So I'm going to get ones from IK up to IK plus DJ minus 1. Right? And then another very rough estimate there, right? So this sum of terms is at least the number of terms times the smallest term. And we're even putting an estimate on that. So just naively, since the sum of the DJs has to be 2k, DJs for sure is less than square root of 2k. Right? So we get this estimate here, right? So and then I can rewrite that to get an upper bound on DJ. All right. So DJ is bounded by AJ divided by some factor which depends on IK. All right. So it's okay. Nothing complicated, but a little bit tricky. All right. Okay. And then then you plug this estimate back into the sum formula. So now I have upper bounds. Is this making sense? Okay. Anyway. Right. So I plug this back into the sum formula. 2k is the sum of the d squared plus d. Okay, we plug that in. But now, right, so just, all right, so again, a very rough estimate. But now what I'm doing here is plugging in my upper bound for di, right? So the upper bound, just go back a second here. Right, so that's the bound for the di. Di squared is going to have an aj squared on the top, but then the sum of the aj squareds is roughly the volume. Okay, so you plug all that in, and then we get this. Right, so again, using the fact that the aj is squared to twice the volume, we come up with this estimate, which rearranging it is the same thing as an upper bound on a squared I plus this little n bit. But okay, so what's it saying? So it's saying that a subscript ik plus a little bit has to be small. But since the a's are a decreasing sequence, that's the same as saying that I has to be big, which is exactly what I want. Okay. So, all right. So you trace this around. Exactly how big does it have to be? So that's the expression. So now, by the way, so now C is kind of capturing a lot, right? So all the volume terms are getting included in C. Whichever other terms we get from the square root of K, they're all being built into C as well. Okay, but that's it. But that's my lower bound on IK. And then you can, then you can feed that into the estimate for EK. And that's it. It's okay. So that's what was required. So that's what we're supposed to be proving. So this is an upper bound on the error term for this domain X, right, in terms of K. Right. So it's giving the growth of the error term in terms of K. All right, and that's it. So that's really our estimate. So it's following exactly from the right, basically just disjoint union property plus the computation for balls. All right, okay, but this is okay. So it's right, but this is a very nice estimate now, though. So okay, I'll write it again. So now I want to use this hypothesis that P is less than 2. Right. So remember P, right? P is defining the domain X. I wanted P to be bigger than 1 to get a domain of finite volume. P less than 2 exactly means that this estimate on the growth is going to be at least K to the Q, where Q is greater than a quarter. Okay. So in other words, these error terms are growing faster than any bounded domain with smooth boundary. Okay. All right. So now we want to kind of enhance that a little bit. Right. Okay. So what's right? So what do we have to prove here? Right. So now we can just sort of work out the packing obstructions. Okay. So it's all right. So just take right. So suppose we have a just for convenience, it's to say a finite collection of domains, and suppose they satisfy this this estimate where the growth rate is well. So the growth rate is less than oh well. Okay. At least right. So I need to say that ek is bigger than minus ck to the quarter. Right, so that's all that's needed here, right? But a lot of domains satisfy that. Okay, then okay, another assumption we suppose the total volume of the di's is equal to the volume of X. Then we can apply the disjoint union property to the union of the di's. Okay, so it's all right. So I'll plug that in. So I'm trying to obstruct embeddings from the union of the di's into X. Right. So I'm interested in the ECH capacities of the union, the disjoint union of the di's. All right. So you plug in the disjoint union property. Okay. So I'm just writing that out. Right. Then capacities you can write in terms of the leading asymptotics plus the error term. Okay. So now to get rid of this maximum, I need to make a choice of ki, and the optimal choice is somehow choosing ki to be roughly proportional to the volume of di. Okay, so that's the formula. So if you choose ki proportional to the volume of di, then you get right when you take the square root, you get the volume of di coming out as a factor, and since the sum of the volumes of the di's is equal to the volume of X, this whole formula simplifies. All right, so that's it. So in other words, we get, if we have the error estimate on the individual domains di, I also get the same sort of growth on the error estimate for the disjoint union. All right, so that's my, right, which is, so that's the conclusion I want. All right, so now we have everything. So now that's proved stuff at this point. All right, so now, okay, right, so just to recap. Right, so from the introduction, another result of Michael Hutchings, of course, very motivated by his papers here. If you take a bounded domain with smooth boundary, then indeed the error terms are bounded below by minus ck to the quarter. Well, we looked at this. Actually, you can generalize this. So this same results we claim holds for, in fact, any compact symplectic manifold with smooth boundary. Or, well, if we're interested in domains in R4, even bounded domains with piecewise smooth boundary. All right, so it holds for things like simplices, polydiscs, all that kind of thing. Okay, so right, so we have that so the domains I was looking at on the previous page, a lot of domains fall into that category, right? So anything with smooth boundary, or you could also look at simplices and things, polydiscs, fine as well. All right, okay, so the previous estimates, right? So for our X, I have an upper bound on the ECH capacities, all right? So, right, but this is already an obstruction, right? Because for the union, right, going back, for the union of the DIs, I have that the ECH capacities are greater than, right, this volume term minus CK to the quarter, right? For our domains, they're less than the same volume term, but then I have minus K to the 1 over 2P, and K to the 1 over 2P is less than, sorry, is bigger than K to the quarter, right? So I have faster, right, I have faster growth on the EK, which means the CKs of X are going to be smaller, hence no symplectic embedding. So, okay, so just a little bit careful here. So this is no volume preserving symplectic embedding in principle, but if we think how it's being proved there's no symplectic embedding because some ECH capacities for X are strictly less than the corresponding ECH capacities for the union of the DIs, okay? So in other words, there has to be a strict inequality on some ECH capacity, and therefore you can replace the DIs by a small rescaling is also fine. All right. Or if there's some of the symplectic manifolds, just scale the symplectic form a little bit, and it's still going to be obstructed. Okay, which is exactly what we need to prove that in this case all packing numbers are strictly less than 1. Right. Okay, and then, well, probably I should have said it earlier, but also out of this, it's also true that X is not symplectomorphic to a domain with smooth boundary. It's not symplectomorphic to a domain in R4, even with piecewise smooth boundary. Because if it was, then the error term would grow like, well, it would grow no faster than k to the quarter, where we've seen that the error term for X has faster growth. So in fact, so you can obstruct a lot of stuff. All right, so that's anyway. So that's it. So in a sense, it's so all the information is there. But anyway, it seems right. It seems new information that you maybe can't see from maybe a single capacity calculation. All right, so that's really okay. Well, that's essentially that's all the main proofs. So I'll just whistle. So there's the boundedness issue. Well, okay, so a little bit about this. This is just completely concrete, right? So we don't need any capacities for this. We can just show that it's a bounded domain just by general kind of general symplectic embeddings. If I have 2 minutes, I have to show you a bit of this. Right. Okay. So in fact, right. So any domain defined by it doesn't have to be concave. It doesn't have to be convex now. Just any domain defined by a decreasing function. I'm writing it in this form just to emphasize. I want to use Z and W coordinates now. So I'm thinking of X as a subset of C2. I want to use ZW coordinates. Right. So if you take any decreasing function, we just normalize. So it takes the value 0 at 1. The area under the graph is finite, right? So in other words, the volume of the corresponding toric domain is finite. Then I claim there's a symplectic embedding into a bounded set. So this is completely explicit. I guess the interest is you can kind of see how bad the boundary is going to get. All right, so I'm saying it embeds into that. So it's not a symplectomorphism. In fact, we know it's not symplectomorphic to such a domain because this polydisk has piecewise smooth boundary. So maybe there's some interest in this in just seeing what it looks like as a bounded domain. So anyway, so you can do this, right? So there's a couple of slides on this then. Right. So what you look at this is S is an open subset of C. It's just really the positive x-axis with an infinite union of 1 by 1 squares. All right. It has infinite area, therefore it's symplectomorphic to the whole complex plane. And the first step is just to map the Z plane into this set S, right? So I want to do it, right? So I want to map the complex plane into S, and I want to do it so points close to the origin in the complex plane are getting mapped as far left as possible. Okay, so I'm going to draw that. So that's, okay. See that there? Okay, so that's, so all these teeth going along the x-axis, that is my region S is a neighborhood of that. And then these arrows are supposed to be illustrating what the fibers are over various points in S. Okay. So for instance, the origin in the complex plane is going to be mapped a long way to the left. And right. And then if we think, okay, sorry, just go back here. If we think of the definition of the domain, so this is like saying that if I'm thinking of this as fibered over the Z plane, the W fibers sit inside disks of area F of pi Z squared. All right. So it's all right. So in other words, so if Z squared is small, the fibers are going to be in, well, so the origin would map a long way to the left. The fiber over the origin is contained in the disk of area F0. But as you move out, as you move into sort of larger annuli in the complex plane, you're going to have to be mapped into teeth further to the right. And therefore, the size of the fibers is going to start getting proportionally smaller. Okay. Well, I'll spare you the exact calculations, but that's more or less how it looks like. Right. So over the second tooth, the fibers are contained in a disk of size F1, third tooth, disk of size F2, so on. Okay. Right, now some notation here. Okay, all that. Right, dA we've already had, just a round disk. RK, these are just partial sums of the FK. But remember, the FK is it's a convergent sum. All right, so it's so I can assume that all of those partial sums are less than V plus 1, say. Okay, then there's a corresponding sequence of annuli, sort of concentric annuli. Okay, and then the point of this is I can find a disk of area FK contained in the annulus AK. All right, so that's essentially what I'm saying then, right? So that's what I'm doing with the disks. So the disk DK is a disk of area FK. And I just want to arrange these disks to kind of be disjoint and sort of sit outside each other. All right, so that's kind of the picture I have in mind. But all of this happens inside of a bounded set. Right. In fact, inside of a disk of area V plus 1. Right, okay, next. Okay, then there's Hamilton. Right, now I want to choose Hamiltonian diffeomorphisms. So psi1 takes the disk of size, the round disk of size F1 into the disk D1, okay? And then if you compose that with psi2, it takes the disk of area F2 into D2, all right? And then you keep iterating that, okay? So what's going to happen here, okay? So D0 has area F0. Inside D0, there's a disk of area F1. Psi1 takes that into D1. And then, okay, then you compose with psi2, and then a smaller disk of area D2 is mapped into the disk D2, and so on and so forth. Right? So we have a lot of Hamiltonian diffeomorphisms, whose composition map the round disks into these sort of surrounding disks. Okay. All right. Okay. So, right. So this is the Hamiltonian diffeomorphism I want to look at. All right. So it's yeah, more complicated than I thought. It's okay. Right. So that's the Hamiltonian diffeomorphism I want to look at. So the chi's are cutoffs, right? So chi is 0 when x is less than 2k minus 1. It's 1 when okay, right, I'll wind this up here. Right, it's 1 when x is bigger than 2k. So, okay. So the upshot of all these Hamiltonian, maybe I'll just tell you what's going to happen. So this is an infinite composition of Hamiltonian diffeomorphisms, but only finitely many of them act at a particular point. All right, so once you know what x is, only the first, if x is equal to 2k, only the first k of these things act. So, okay. So we apply that Hamiltonian diffeomorphism, and that's what's supposed to happen, all right? So the projection now is still an infinite row of teeth, but now I also get teeth, over the odd, starting at odd integers, and then these are representing the fibers. So instead of the fibers being round disks, when you apply these Hamiltonian diffeomorphisms, the fibers are now sitting inside these sort of concentric disks. And then, all right, okay, and then this psi is a symplectic immersion, which takes the whole row of teeth and kind of winds them up around that 4-leaf clover, right? So psi is an immersion of the z-plane, but if 2 points have the same image, they have to be like 4 teeth further along. And if they're 4 teeth further along, then the fibers are going to be different. So, okay, so this is the conclusion. So, okay, so psi is an immersion from the teeth into the disk. If you take the product with the identity in the W plane, it's actually a symplectic embedding. And this gets our domain into a bounded set as required. All right. But you can see that the boundary, so this embedding is actually going to be smooth. It has a smooth extension to the boundary of X, but there's going to be accumulation points given exactly by the accumulation points of these DKs as you go further out. Right, so the DKs are kind of accumulating, and that's somehow that's the bad boundary. Okay, sorry. All right, so I'll leave it there. Thank you very much. Thank you.
Any questions for Richard? So maybe I'll. Oh yeah, go ahead.
Mike. Question. Yes, that was a really cool example. I saw you assumed p is less than 2, and I see that you need that in the proof because you need 1/2p to be bigger than 1/4.
Yep.
But I was wondering if somehow someone could prove improve the subleading asymptotics, could you make P bigger than 2?
Right, so P bigger than 2. Well, right. Yeah, I suppose in principle, not true. Oh, so you said right as well. Right. Yeah. So we think. Yeah, I think so. Right. I mean, you're going to have to. Oh, wait a second. Right. Oh, so you're saying so suppose that these subleading asymptotics were like O1 instead of O1/4.
Right.
Right. Yeah, I would think so. Yeah. Yeah. Right. Yeah. Yeah. Right. Yeah. So you just take P. Right. So you can let P. As P gets bigger, our estimate on the subleading asymptotics is going to get worse. But as long as that's less than whatever you get for the DI, I think that's fine.
Okay. Thanks.
Yeah. Right.
So something that I was wondering is, so you've constructed this X, which, if I remember right, is a convex toric domain with finite volume, such that
concave.
All of the,
it's given by a convex function, so it's concave.
Thanks. Such that all of the packing numbers are strictly less than 1. And I was wondering, do you have any idea if this should be thought of as exhibiting pathological or typical behavior?
Well, I don't know. I mean, as far as I know, it's the first example which doesn't have packing stability. But, I suppose now you've seen one. I mean, as Michael's saying, probably, you can produce a lot more. Right, yeah. I suppose maybe it depends if you think things with reasonably smooth boundary are typical or not. Maybe a random thing is going to have very strange boundary, and then maybe it turns out it just doesn't have packing stability. So probably maybe in the set of all symplectic manifolds, it's kind of generic in some sense. But among nice ones, it might still be a bit pathological.
So a related question is, how the heck did you cook up X?
How? Well, I asked Dan if this was true. So yeah. Well, I mean, so initially we just right. So Dan is our resident expert on ECH capacities. So you want to construct something whose ECH capacities are going to obstruct. I mean, we're thinking in terms of ellipsoid embeddings. So you want to construct some ECH capacities which are going to obstruct embeddings of thin ellipsoids. So that's kind of equivalent to packing stability, getting large ellipsoid embeddings. So, okay, so we already knew, I think there's a paper of Dan and Nihil Savale. So the the subleading asymptotics of ellipsoids. You want to concoct something which has subleading asymptotics somehow with faster growth than the subleading asymptotics of ellipsoids. So then you can say, well, what do the weights have to be? And then already you can kind of write down something with non-smooth boundary that's going to do the job. So you just kind of put the balls together and sort of, you can concoct a concave domain with non-smooth boundary that's going to do the job. And then, okay, then we'd like to build it up. And I suppose going back to your question, how unpathological can this get? Then you have to work a little bit harder to try and get smooth boundary and, make it look a bit nicer. But, right, yeah. But in a sense, I guess if you, I don't know, maybe Dan can answer better. But if you know a lot of ECH and you ask the question, then this is maybe kind of a natural way to go.
Well, I think it's been known in the community for a while that the subleading asymptotics can give obstructions to volume filling embeddings. I mean, because that's kind of what they're, by definition, they are helpful for that. So then it becomes a question about what kind of subleading asymptotics you can cook up.
Right. Yeah.
I mean, by definition, they're the thing where you subtract off the volume. So they're pretty well suited for studying whether you have a volume filling embedding or not.
Right. Yeah. Right. Yeah. So I suppose the interview, right. Yeah. So but right. But still, I'd say it's curious that, I mean, first of all, we can actually make the boundary smooth, and it could even be a bounded domain, if you like. So somehow it's, so.
Yeah, I mean, until messing around, I didn't know, for example, whether you could get the subleading asymptotics to be as close as you want to k to the 1/2. Like, the leading order asymptotics are like k to the 1/2, and for example, Michael's result is that if the boundary is nice, they no worse than k to the 1/4. But before this, it wasn't clear to me whether you could get the subleading asymptotics to be as close as you want to k to the 1/2. But that's what Richard was saying with the p and stuff.
Any more questions for Richard?
Yeah, so
I just have a quick question. I was just curious. So like a lot of what, you could imagine kind of the analogous example in higher dimensions with, just cook up some similar looking function, unbounded toric domain. Do you have any opinion about whether the analogous higher dimensional domain would also fail? I mean, obviously in that case, you don't have ECH capacities anymore, but you could, there's other capacities with a lot of the same properties that you were using, like disjoint union bound and so on. So
there are. Oh, you're asking, are there? Oh, right. I mean, yeah. I mean, as far as I know, right. Yeah. I mean, sometimes there is more flexibility in higher dimensions. It's not obvious that you could get counterexamples in higher dimension. It's right. Yeah. I mean, right. I mean, okay. If there were some capacities that had similar kind of, if we could get, if we could use other capacities in similar ways, then maybe. But to me, it's not obvious it's going to be true. Sometimes higher dimension, you have more moves, symplectic embeddings, more flexible. So maybe, who knows? Maybe it's completely not obvious to me. I really have no idea. There's no right. I mean, I think there's no counterexamples. Probably it's true to say there's no. If anybody knows any. I think there's probably no known domain of dimension now bigger than 4, which doesn't have packing stability.
Mm-hmm.
I mean, when you think about it, I mean, you could easily guess any closed manifold of high dimension might have packing stability. Yeah, I mean, that's right. I mean, I guess that's a small class, but yeah, I don't know. Yeah, if you could produce, right, yeah. I mean, right. I mean, this proof is very formal in a sense. So we need capacities with the right properties, to get the results. So,
yeah, I mean, I think there do exist capacities which have the same disjoint union bound, but they don't have the same asymptotics. So I don't know if they would be, the main obstruction wouldn't be clear how you analyze that. But.
Yeah, I'm not sure. I mean, I suppose conceivably you could even obstruct this with first order asymptotics if the capacity to see the volume would be sort of surprising.
I mean, what I was wondering is that in higher dimensions these kind of capacities don't recover the volume, but in some ways that seems like what you want in this case. Like usually it's
as long as the inequality, yeah, exactly right. Yeah. As long as the inequality goes the right way, I guess.
Yeah. So.
Yeah. So, right. Yeah, but potentially it'd be interesting to check. Yeah, I don't have any intuition on whether it's going to be true or false, but
I see. But so yeah, it could just be some sort of first order information of some.
Right. So I mean, right. So if the first order information gives the wrong bounds, then you're it's hopeless, I guess. And right. I mean, you need the first order information of the disjoint union to be at least less, or to be less than or equal to the first order information of your X.
So if I recall correctly, one can make some capacities in higher dimensions that recover the volume, but in kind of artificial way, you just sort of define them in terms of which ball packings are possible. So you're sort of redefining the question. So it might not help with your problem, but you can make capacities that recover the volume, I believe.
Okay. Right. But they're kind of set up in a certain way. So, yeah. Okay. Well, that's okay. So maybe it's not hopeless then. I mean, I have no idea how to prove packing stability for all 6 manifolds. I mean, as well. So it's
So, folks, I have to run. I'm going to say goodbye, but please feel free to keep chatting if you'd like to do that. And thanks a lot for the beautiful talk, Richard.
Well, thanks, Nate. Yeah.
Bye.